Bismillahirrahmanirrahim. Assalamu alaikum guys, how are you? Hope every one of you are doing very well, as just you have one more day to appear in the examination. And many of you students have sent me some emails and text messages that they are getting some problem with these numericals, and I think many of you have problem with this cracked transform section, as we have focused more on the uncracked sections in the class during our lectures. And I think we were not able to give a lot of attention to the correct section. So here I'm just trying to give you a detailed overview again for this correct section. Let's see, have a description of this example that we also do, that's also available in your lecture notes. It said that we have a rectangular beam, and with the size is given, and its effective depth is also given, and its reinforcement with three reinforcement, that's number 25. And then its concrete specified compressive strength is also given here. The yield strength of steel is also known to you. Let's just get some pointers so we can make a good discussion of here. Oh, let's see. So we first write down the data. If you see here, this is our diagram. That is, you can say just a beam cross section is given here. Here it is the B, that is width of the section. Then it gives you the effective depth D. But you see, this dimension is not written over here like this one. But this total depth of the beam is given as 650 mm. So keep it in mind, don't get confused that this data is not given, so it's actually available to you in the statement. Further, what is known that these steel bars, so these steel bars are also known you to that there are three steel bars and each is number 25 here. So you have to find out the area using this description. So using this description, this number of steel bars, I have provided you also some tables to get out, to find out the values of the area. So you will be using that table to find out the area of one bar of this size. Then you would multiply it by 3 to get the total reinforcement area. Further, is given that compressive strength of concrete is 28 megapascal. Here you write here. Here we write it here, FC prime, this as 28 megapascal. Further is the yield strength of steel, that is we represent it by Fy here. You see it's 420 megapascal. Further, the modulus of rupture, that in terms of tensile strength, that is given to be a maximum of modulus of rupture is 3.25 megapascal. So in question we are asked to determine the stresses. Stresses we are not specified here, where we have to find the stresses. So normally we find the stresses at extreme fibers. That extreme fiber means upside and downside of the section, and normally we can find out the stresses at the the reinforcements. But when you are asked to find out the stresses, it must be understood that you have to find out the stresses at the top the fibers and the bottom fiber. So we will be finding the stresses at the top fibers and bottom fibers, and the thing is given to us is the this moments, this bending moment, that's 120 kilonewton per kilonewton meter. So this is the geometrical description of the section available to us, and further loading and description of the material properties are also given. Now we have to find out these stresses. So how we will proceed to this? Let's see for here. We have a cracked transform section. As you know, you are very familiar with the cracked transform section. So this is our correct transform section diagram. I come to you this point. We are assuming this, as you remember, we are assuming this specifically. We're going this as a cracked transform section. So as a cracked section. So that's why we didn't show here any reinforced concrete here. So you see here concrete is missing. So it means this area is cracked already. And this area that you see shaded area, this is uncracked region. So uncracked region have the same width as original section, but how to find out this depth? This depth is important to know, that how much is this depth of uncracked region. Further, you see here Here you see this is n times of area of steel. Make it very clear. So this equivalent area is equal to n times of area of steel. But when you do in the uh, uncracked section, there it was n minus 1 times of area of steel. And I have given you a bit about this, that why this is n minus 1 and this is n here. So moving forward to the solution, let's see. First we must know the modulus of elasticities of the both materials. In every question and every problem you must know. And as if you remember, I have asked you to memorize or just note down the modulus of elasticity of steel. So hope you remember that. So for modulus of concrete you can use this formula, because every your concrete's compressive strength vary from side to side, so better to use this formula. Fc prime is compressive strength is given to you in the question, so using this formula and Fc prime here you can find out the modulus of elasticity of concrete. So I teach you the modular ratio. You are very familiar with the modular ratio. So once you find the modulus of elasticity of steel, and you find the modulus of elasticity of concrete, so you are easily can find the modular ratio. And here one thing more that we are going to find, that is the steel ratio. This rho is called the steel ratio, and steel ratio is area of steel divided by the the area of the section. So here this is B and this is our deep depth, effective depth. So the steel ratio is this is just area of steel, that is 1530. This is how area of steel, that is you have three reinforcement bars. Each reinforcement number 25 bar is I think about 510, I guess. 510 multiplied by 3 give you 1530. Yes, I think it's 510 for each number 25 bar. So once you multiply it by 3 you get 1530 mm square. This is the area of steel, that reinforcement that is inside your section, and here it is the area of the section. That is, make it clear, it's not area of actually the section, it is the effective area. You see here we use the depth, effective depth. We didn't use the total depth of the section. Make it very clear. So we are using here the effective depth. So here, oh, sorry guys. Okay, sorry man. So here we are. Yes, so here we find the steel ratio. Simply you find calculate this one. For the n times of rho, we are just actually going to find out this value of k, this very value of k. If you remember in the previous slides lectures, we derived a formula for k. So that formula is here that we are just going to use now. So for this we need to find out n times of steel ratio, that is modular ratio. So using this formula we know the n value of n here, we know the value of the steel ratio here. So using this formula we just use this all the stuff, you can just find out this value of k. So this is just a factor value k that is here. So actually this depth, this uncracked depth is equal to 0.33 multiplied by total this effective depth d. It would be this 196. Actually this 196.5, this 196.5 is actually total this depth. How come this 196.5 is just multiplied by 0.33 with 590, I think is 5 yes 590. So you just try this one, you will get 196.5. So here this is the uncracked depth. Further similarly we have to find out the j value, this vector j. If you remember in the diagram we show here, let's say here is our compression zone, here is our tension forces, so the distance between these two is jd. So similarly like k we have to find out this value j, this is jd. So j is equal to 1 minus k over 3. So k we find over here 0.33. So 1 minus it comes to be 0.889. So JD will come to be, you multiply D again with this value 0.889, so you will get the JD. Let's know, as we have considered this the cracked sections, so we know we will take all the things, all the stuff at the neutral axis. So neutral axis shifts normally at the the location of the depth. Neutral, this is the location of the neutral depth, where uh, the depth to the depth of the cracked section, uncracked section, that is the location of the neutral axis. So here is the location of the neutral axis. Now this one is here, the location of the neutral axis. Now we're trying to find the moment of inertia at the neutral axis. So as you remember, I told you about the moment of inertia and all this stuff we tried. So this is first BH cube. So this is our one section, this uncracked section 1. We are just trying to find the moment of inertia of this uncracked section about this neutral axis here. See here the cursor, this is the neutral axis. So the depth width is the B, that is 250, that's given, and this depth is 196. So the formula is BH cube. So this cube over 12 divided by, so this area again, this come to be 250 into this one, and here is the centroidal distance from this neutral axis. So centroidal distance of this shape, this very shape from the neutral axis, is just half of this KD, and the KD is our 196.5. so half of this one here, the square comes to be. So this whole stuff is for this uncracked section here. So for this section, there is the covalent steel we put here. So for this is the area here, area of this section. Sorry, it's not clear. Yes, this is bit better. So this area is equal to modular ratio times the area of steel. So here is the modular ratio, your 8, and the area of steel comes to be 1530. So you just multiply this, you will get this one area. Then again here is this. So now we have to find out this the centroidal distance of this very part to the neutral axis, this thing. So this anyhow, sorry, I just got a call, sorry. So to find out the centroidal distance of this shape to this point here, you see we know the value of this D value from the top here. So and we will subtract this one here, this 96. So from top we have reached to this point now, subtracting the value of this one D, that is from this center. Actually we have to go from this center to this level. Maybe I can try again for you. Actually we have to find out this the centroidal distance of this shape is from center here to the neutral axis level, and the neutral axis level is just here. So to reach this neutral axis level, we know this value of D, and we also know this value of KD. So if we subtract uh, this KD from D, we automatically reach to this level. So the same is here. Sorry, 590 is this depth, and this 196.5 is this KD value. So we are just subtracting this one to get yes, this value. So we get this value over here. Is it clear? I hope it would be clear now. So this all stuff, this is the area and the other moment of inertia and all of this stuff. One thing more here I want to add to you is this: we didn't write here moment of inertia. You see, it is just area and it's just AD square. We didn't add the moment of inertia here. Actually we neglected the moment of inertia because this very thickness is very small. So if we take the moment of inertia of this thickness, so it will be very small amount, so it's just negligible. So we just remove this value and we just write AD square. Okay, hope you can find out this numerical value. So next is, if you remember, we stitch the formula, flexure stress formula, that is here again, that moment is equal to ASFSJD. So here AS is the area of steel, Fs is the stress in the steel, J is, you know, the this one, the JD. Yeah, yes, JD. This is the, you know, the lever arm between compression and tension forces here. So here we find the Fs. So that's tension in the steel here. That is actually the steel here. Basically, we have replaced this section with concrete, but there is actually a steel. So the steel here existing here, we are just trying to find the stresses in this steel. So this Fs would be the moment, that is the bending moment given in the question statement here, area of steel that we have find out using that table and multiplying with the number of steel bars, JD. The JD that we have calculated just above here, we find the value of J and then multiply it with the sorry effective depth D. So ultimately you will find this value here. Is it clear so far? I hope it will be clear. So this is the stress in the steel wire. So moving forward here, so that was the actually stress developed due the this stress that we calculated is the stress developed due to the given geometrical and loading conditions. Means geometrical conditions of this, you know, the location and all the stuff of the sections, then we have material properties given there, and then the loading. So because of all these stuff, so this is the developed stress over here in the steel. But here this is the permissible stress that can so this is just a code value. That means ACI code recommends that a steel can take maximum stress to this level. Means a steel reinforcement can take maximum 168 megapascal if we are using the steel of given Fy, that is 420 megapascal in our question that is given here. If we are using this kind of steel, so for this the maximum permissible steel in the is this one here. But in general, let's say if you have experienced any value, any steel whose Fy is more than or anything other than 420, so it will change accordingly. So this is 168 megapascal. Sorry, here we calculate 149 megapascal. So it's 149 megapascal here. You just keep it, remember it, 149 megapascal, and here is 168 megapascal. So 149 is less than 149 is less than 160. Sorry, it's not writing very well, so just understand. So 149 is less than, you know, the 168 megapascal. So we can say the steel stress developed in the steel is just in the elastic range. Is it clear? So the steel stresses develop in the steel that reflects that our steel is still in elastic range. Now coming toward the concrete section, that is top section, you know, compression section in other words you can say. In compression section, so the same formula again here is the previous formula, but it's in terms of concrete now here. Fc is equal to times of moment over kg bd square. So actually it is like moment is equal to Fc into like this formula again. I can give you here this one here. You just reform this formula, means you just put the value of J. So J is equal to, from here you can put J is equal to 1 minus K by 3, or so in terms of KD you can use this formula. Alright, this is the area of concrete. You would use this area of concrete. Steel stress will be Fc, and then the moment and the value from the, you know, the here lever arm will be changed accordingly here. So it comes to be Fc is equal to m over kg bd square. So just put the value of m, k and j, you know, here you put the value of j here, then b and d square, you will find this value. Then here again ACI code sorry, here again ACI code have some recommendation. So here ACI code recommend in case of concrete that it should not increase from 0.45 times of Fc prime. So this value is 9.32 megapascal, that is less than 12.6. It means our concrete on the top surface is quite in a good range. It's on a safer side. In other words, you can say it's in a safer side. Our calculated value is less than the maximum recommended value or the maximum permissible value. So let's say we have the another bottom section. Our bottom section, there is tension concrete. You see here CT clearly is written here. This means the lower part, the neutral axis, that is that in the figure we see that is we assume that is cracked. Now we have to check either it's really cracked or not cracked. So we take it as the bottom tension concrete area. So for this we just use this formula my over I. That's just a moment of inertia. We calculate it for the shape here. That is just moment, the bending moment here, and the y is the distance again from the bottom here 650. The now here we didn't take the effective depth. So you see it's the previously, if you remember, here we take the area in case of the here this one is in the case of I mean this transformed section for the reinforcement, but here don't forget we are taking these values for the concrete section that is supposed to be cracked, this section here to this level. So this is the concrete, all this one is the concrete. So now we are just trying to find out the stresses developed in this section. Sorry. So so for this section this is the moment bending moment applied here, because this 650 minus 196 is again we are just taking this 650 is, if you I can just draw again for you, maybe you are confused about this. I can just make a draw here. This is one section here, and I should change the color also, so make it very clear for you, don't get confused. So you see this section was uncracked, this section was uncracked here. So here I just make this area shaded with the horizontal lines, and I can just draw here the vertical lines, so you can just understand here that the horizontal lines, the area with the horizontal line is the compression area, and this the with the vertical line is the tension area. Here this red line you see here, this red line is the neutral axis. So we are just trying to find out this one. So this the centroid of this area from this point. So what we know here is that we know this depth. This depth is the section depth, that is 650 mm. Then further what we know is that we know this area here. So we know this area, this one, this length, sorry, we know this length, so we can find this length easily. Is it clear? I hope you will be very you can just find out this depth, how much this depth is. So further is the moment of inertia, I think we have calculated previously. So just using this relation you can find this, the tension beam or the tension stress here, strength in the load structure. If you just if you see here, it's compared with the modulus of rupture value that was 3.5 megapascal given in the question. So it is much more than modulus of rupture. So this shows that the section have been cracked, because the capacity, maximum capacity of this area that recommended was just 3.5 megapascal, as it has been increased. Sorry, as it has increased the 3.5 megapascal, so it means the area have been cracked already. Is it clear? Okay, so if you have I try to just make it clear for you. If you are still confused, you can use again, you can just send me an email, I would respond you inshallah. So if you are really very confused, you are not very sure either you got it or not, on the Monday you just come in the morning at 9. I would be in office at 9 inshallah. So you just give me a call or just ask the security guard to call me out, so I would come to you and I would explain you again. So anytime, as much time as you wish, I am available, so there is no excuse on your side that I was not available or anything like this. So I think this was one was the uncracked transform section, and I have this explained this stuff to you already in the class is in much details. I think we spend most of our time on this section. So if you still have some problem in here, even then you can discuss me, or you can just give me an email. Yes, one thing more here, I just want to mention here. You see here that in the previous slide we just make a check, so same is here check. let you see 0.45 times of FC you use there in the, that's just example. Again is here is the modulus of rupture check. So don't forget to apply this check. Actually this check help you to know either your your section or your the thing you are just going to study, is it in the safer side. It means if it is less than these values as recommended by the code, so it means you are on okay, you are okay, your section is okay, so no need to worry. But it here is proves that this section is in compression, and here as it is again less than modulus of rupture, so it shows that there is still a tension. If let's say this comes to be like 4.20, so it would be definitely more than more sorry, let's say it's 4.20, so it would be more than modulus of rupture, that is 3.5 megapascal. So this section should be cracked. Let's say, I repeat, if the bottom stress comes to be more than the modulus of rupture, it means it's cracked. Another, this is the steel stress again here. How to find the steel stress here, and then compare it with the the yield stress of the steel that's given in the question. So here you see in the crack transform section we use n times of area of steel. Here we are using n minus 1 times of area of steel. The reason why we are using n minus 1 times of area of steel I have explained in the class in detail. If you are still confused, so you just drop me an email so I could respond you accordingly. Hope you have enjoyed all this stuff, and it would be very clear to you now. So you still have and find any question you, I think some student of you have sent me an email, so I have to reply to those emails as well. So yes, you see here is one email, and that is it. So once you just go through this one, if you found any problem, if you face any problem, you just drop me an email. Okay, wish you all very good luck for your exam. See you on Monday inshallah. Allah Hafiz.